Okay, good morning all. So we'll start with the class. And if I just go back to our previous class, we were dealing with some problems which are related to finding the stresses in the composite section. Maybe I had asked you to find the solution in this case, right? So even if this problem is repeated, just you can just go through this. So if you have this bar and if the extension, there was a bar of 4-meter length and 40 diameter, and they were asked to determine what should be the length of this bore, okay, this hole which is drilled in the bar, if its extension is to increase by 30%. So first we have determined what is the extension without the bore. It was 0.637, and after providing the bore, that is after drilling this hole, the extension should be 30% more than this. So that is 1.3 times this 0.637. It comes out as 0.828. And there we are determine the deformation of the two parts. Now we are considering this bar in two parts, one without the bore portion, another with the bore portion with this drill bore. So what is the extension? We have been expressing in terms of x. Let this bore length be x. So what I have is this will be load PL by E, P 40 kilonewton into L will be now 4 minus X. If I consider, take it in terms of meter because I want all the units to be in mm. So I'll consider this to length in terms of meter, then later convert them both together in mm by multiplying 10 raised to 3. P into L 4 minus X into 10 raised to 3 divided by E for this unbored portion, solid portion. Then for this portion where we have provided the this bore, we have drilled this bore, it will be, the load will be same, length will be this x because this is the length of the bore portion. So this x into 10 raised to 3 in terms of mm divided by E. What is the area? It will be area of this hole, pi by 4 into this, this hollow portion, pi by 4 into 40 square minus 20 square. 20 is the diameter of the bore, what has been provided here. So what you have, these are the two deformations in this bar for the solid portion and for a hollow circular bar. Now when you add up these two, it should come out equal to this 0.828. Okay, so when I add these two and equate them to 0.828, my x value comes out as 3.62 meters. So this is the length for which this hole has to be drilled. So I hope you have got this answer. If you have tried solving that, or if you have any difficulty in that part, please let me know. Is that fine? Okay, now one more problem in this case. So what you have here, there is a rigid bar, okay, this ABCD, and is supported at A, at this point A, by means of a hinge, and also it is connected to two wires, steel wires, this BE and CF. Okay, so once a load of 90 kilonewton is applied at the end D in this way, what is the deformation in these two wires, or the tension in these two wires has to be determined. Okay, so a rigid bar ABCD is hinged at A and is supported in a horizontal position by two identical steel wires as shown. A vertical load of 90 kilonewton is applied at D. Find the tension in the two wires. You have to find the tension in these two wires. So length of two wires is 1.5 meter. Both are of 1.5 meter length. And it is told they are identical. Means they are of same material and same cross section. Okay. So keeping that in mind, we need to determine what is the uh, force or the tension in these wires. 59. So I given some starting this one for that problem. With that, can you find out what is the tension in those wires? What is there is when you have come across this problem earlier. If it is solved, please let me know.
No, sir.
Okay. So here, what you have is it is a rigid bar. That is, once you apply this force of 90 kilonewton at this end, it is going to be straight only. It will not be bending in a curved manner. So what you have, once you apply the load, so this is the deformed shape. This is the shape in which it will be bent or it will be rotated. So under this circumstance, let us say delta 1 is the extension of this steel wire BE and delta 2 is the extension of this steel wire CF. Okay, so what I can consider now is there are two triangles, similar triangles over here. One is this A and this B dash. Another is A, C and C dash. Okay, so these two triangles I am going to use for relating my deformation in these wires. Okay, so that is what I have done here. So this delta 1 by delta 2, okay, height of the two triangle, these ratios delta 1 by delta 2 should be equal to ratio of their base. Okay, so that is 2 by 4. Delta 1 by delta 2 should be equal to 2 base of this triangle divided by base of this larger triangle, 4 meters, 2 by 4. So this tells me what is the relation between delta 1 and delta 2. What I get here is delta 1, 2 into delta 1 will be equal to delta 2. Okay, or delta 2 is twice the delta 1. This is one relation what we have at this point now. Okay, now what we have is what is the deformation in the wires. I can write for expression for that. What is the expression for deformation in any member? We have this expression delta equal to PL by AE. So the same has been applied for the wire BE and wire CF. So what happens? This delta 1 deformation in steel wire 1, that is in PE, will be P1 L1 by A1 into E1. Okay, so this is the force in the wire BE, length of wire BE L1, area of cross section of this BE, and modulus of elasticity of BE. Okay, so since the two wires are identical, for both wires A and E will be same, and also the length of the two wires is 1.5 meter. L1 and L2 they are same. So this deformation expression is used for wire BE as well as for this wire CF. Okay, so this is one expression what I'll get on substituting for these P1 L1 E1 E1. Okay, I don't know what is P1 here. I have to determine this P1. Other than P1, L1 is known to me. A and E are constant for both the wires. Okay, I'll just substitute them as E. Then same if I use it or apply it for second wire, that is for wire CF, delta 2 will be P2 L2 upon A2 into E2. Okay, so L2 is 1.5 meters, same the length 1.5 meter, that is what is given to us. Okay, P2 will determine that. AE they are constant, they are same as which that of for wire 1 or the wire B. Okay, so this will be one more this one. We have expression in terms of unknowns now. So when I go for simplifying this, okay, so what I get, so deformation in first wire that is 2 times delta 1 will be equal to delta 2. This is one relation what we obtained from that similar triangle relation over here. 2 into delta 1 is equal to delta 2, or I use this expressions what we wrote for the deformation delta 1. What is delta 1 and what is delta 2? So this and the relation between delta 1 and delta 2 has been used. Okay, so what this tells us is, on cancelling the terms AE and also this 1.5, you'll get it as 2 times P1 is equal to P2. Okay, so 2 into P1 is equal to P2. That is what you are getting, the relation between the forces. Okay, this is the relation between force in wire BE and wire CF. Okay, now what you can do is, we can go ahead with another equilibrium condition. What should happen is, summation of moment should come out to 0. Okay, so if I take summation of moment of all forces about this point A, okay, so summation of moment of all these forces which are acting on this rod or on this bar A, B, C, D, okay, they should sum up to 0. Okay, so what we have is, at the end D we have a force of 90 kilonewton which is acting in vertically downward direction. So this will have a clockwise movement about this point A. Okay, so 90 into this distance 6 meter, 2 plus 2 plus 2, 6 meter, 90 into 6. Okay, that should be equal to all the anti-clockwise movements. What are the forces which are causing anti-clockwise movements? P1 and P2. Okay, so P1 is also having a anti-clockwise movement about point A. Even P2 is also having an anti-clockwise movement about point A. So I have taken that. So P1 into 2 meter distance plus P2 into 4 meter distance, okay, here should be equal to this 19 to 6. These P1 and P2 are producing anti-clockwise moments. So sum of anti-clockwise moments is equal to sum of clockwise moments. That is what is equated. Or even you can take it on one side, entirely everything on one side, and equate it to 0. That can also be done. So if you do that, this is what you will get: 90 into 6 minus P1 into 2 minus P2 into 4 should come out to 0. Or this, on rearranging this, you are going to this get this equation. Okay, so this will tell you what is the force in the wire B and wire CF. So what we'll get is, P1 is 54 kilonewton, P2 is 108 kilonewton. Just do this calculation, check it from your side, see whether you'll get the same relations. I hope it is clear what we did for finding the forces in the two wires. The first thing was this rod which was there, ABCD, hinged at A and connected to two steel wires at B and C. Okay, so at end D, 90 kilonewton downward force is applied over here. What you have to find is, what is the force in these two wires, BE and CF. Okay, so this is what, this is our uh, sh rotated shape of this steel rod. Okay, so once you consider this rotated connection, sorry, rotated shape, so from this I'll be able to get the relation between delta 1 and delta 2 by considering the two similar triangles ABB dash and ACC dash. Okay, so that gave me delta 1 by delta 2 is equal to 2 by 4, or 2 times delta 1 is equal to delta 2. This is one relation what we obtained. Then we went for writing the expression for delta 1. So deformation in any member delta is given by PL by A. Okay, so that is applied for wire B and this wire CF. Okay, P1 L1 by A1 E1, and for CF it will be P2 L2 by A2 E2. A1 E1 and A2 E2, they are same for both wires. Let that be AE. Okay, L1 and L2 both are of 1.5 meter. So that has been substituted. So on doing that and using this first relation, this is what we will be able to obtain. We will be able to obtain the relation between P1 and P2, the forces in the two wires. P1 in the wire B and P2 is the force in wire CF. Okay. Now we considered the moment equilibrium. We took moment of all the forces acting on this rod ABCD about this point A and equated them to 0. Okay, we did that, and what we got is P1 and P2 values, force in wire 1 and force in wire 2. So this is what the values are. Are you getting the same values? Any difference in values? Yes. Do you have any other values than this? Let me know. Are you able to hear me?
Yes, sir.
Yes, sir.
So is that fine? This value P1 and P2?
Yes, sir.
Okay. Just try working in this one, this problem. Okay, here also similar problem. A rigid bar of length 0.5 meter and negligible weight hangs by means of two wires of length 1.2 meter each, as shown in the figure. If a load of 100 kilonewton is applied as shown, determine the stresses in the two wires and the inclination of the bar with horizontal. The cross-sectional area of aluminum bar is 100 mm square and the cross-section area of steel bar is 500 mm square. Modulus of elasticity is 202 GPa for steel and 65 GPa for aluminum. Okay, so just like our previous problem, this is another problem. Hello, sir. Yes. Okay. So now in this case, the two wires or the two rods which are attached to this bar. Okay, this is a bar. Okay, what you have here. So this is of 0.5 meter length and it is suspended. Okay, or it is hanging by means of two wires which are attached to it. Okay, at the two ends. So one is of aluminum, another is of steel. The length of both wires are 1.2 meters. Okay, so this is the load what has been applied to this horizontal rod. Okay, so it has been applied at a distance L by 3 from this left end. Okay, the total length is 0.5 meter and this load is applied at a distance of L by 3, 0.5 by 3 from this left end of the rod. Okay, what you have to find is what is the inclination of this bar? What is the inclination of this bar due to this force what has been applied over here in this form? Okay, so that inclination depends on by how much amount these two wires are going to extend. Okay, so what will be the extension of aluminum, whether it is less than steel or more than steel, and what is the extension of steel wire? So let us say this is the extension. So once due to application of load, this may be the extension over here. Okay, so for that you need to find out what will be our this rotation of this bar. You got that one problem? What is the what has been asked? Okay, let's say if it is going to rotate like this, then this value you need to find out what is this rotation. For that, what you require is what is this deformation in aluminum bar and what is the deformation in this steel bar. If I am able to find these two, I can easily find out what is this inclination, because this length is known to me. It is 0.5 meter adjacent side, and here I can find this height of the triangle delta 2 minus delta 1. Okay, so I can express that in terms of tan relation later. So what will be delta 1 and delta 2? First we need to find those two. Okay, so can you determine that? So what happens is this force in aluminum plus force in steel bar should be equal to 100 kilonewton. That is one. Okay, one relation for equilibrium. Along with that, if I take moment of all the forces which are acting on this bar. So what are the forces here? One is this 100 kilonewton, which is applied in vertically downward direction. The other two forces which will be acting on this bar are these forces in the cables or these wires, P1 and P2, force in aluminum bar and force in steel bar. Okay, so if I go for taking the moment of forces about say this end, okay, so what happens, this P2 into 0.5 meter, okay, that is an anti-clockwise movement, should be equal to this 100 into 0.5 by 3. This is applied at a distance of L by 3, that is 0.5 by 3, and this is having a clockwise movement about this point over here. Okay, so what I'm doing is P2 into 0.5, I'm adding all the moments, anti-clockwise movement, plus 100 into 0.5 by 3 should come out to 0. Okay, or just this has been rearranged here. And what it is giving me is what is P1 and also what is P2. I'll be able to obtain this. Okay, so what I have used at the beginning is the two conditions of equilibrium. Summation Fy equal to 0, that is P1 plus P2 is equal to 100, and summation of moments is equal to 0, that is minus P2 into 0.5 plus 100 into 0.5 by 3 should come out to 0. So using these two equilibrium conditions, I'm getting this P1 and P2. Okay. Now knowing this P1 and P2, can you find the deformation delta 1 and delta 2? All other properties are given to us. Please tell me what will be delta 1 and delta 2 values. Calculate and tell me what will be delta 1 and what will be delta 2. I've given you what is P1 and P2. Can you proceed ahead for finding delta 1 and delta 2? Try it. This one idea, you can apply the relationships what you have and find out what is the deformation in aluminum bar and deformation in steel bar. So what I can say, delta 1, like we have used earlier, what you can write is, so delta 1, I can put it as P1 L1.
P1 L1 divided by
Correct.
A1 into E.
Yes. When it comes to elongation of the second bar, these terms will come out as delta 2, which will be equal to P2 L2. This will be P2 L2 by A2 into E2. Okay, so I think we have all these values. We have to substitute for them. P1 P2 we have determined. L1 and L2 are same 1.2 meters, which are given. Okay, L1 and this is L2, right? A1 A2, what do you have? So area of aluminum bar, it is 1000 mm², and area of steel bar, it is 500 mm². Okay, so we also have A1 and A2. Modulus of elasticity for aluminum, for steel it is 202 GPa, and for aluminum it is 65 GPa. Okay, So 1 Pascal, it is 1 Newton per meter square. Okay, or that will be 1 into 10 raised to minus 6 Newton per mm square. If you convert
ಆರಾಮಿಲ್ಲ ಕೆಮ್ತಿರ್ತಾನೆ ನೀವು ಆಟಾಡಕ್ ಹೋಗ್ತಾನ ಅವನ ಜೊತೆ ಎಂತ ಮಾಸ್ಕ್ ಹಾಕೊಂಡ್ ಹೋಗ್ಬೇಕ ಅಲ್ಲಿ ಗಟ್ರದ ಬಾಲ್ ಎಲ್ಲ ಬಿದ್ದಿರ್ತೈತಿ ಅವೆಲ್ಲ ಹಿಡ್ಕೊಂಡ್ ಆಟಾಡ್ತಾರ
So you muted mic, sir.
So
okay,
your
I'm
voice
sorry,
is
sorry,
not
sorry. Yes, it got disconnected. So it is there. Are you able to
Yeah,
find?
now,
Ah,
yeah, now
yes.
it's there, sir.
No.
okay. Can anyone give me what is delta 1 and delta 2? I was just revising that itself. That is summation Fy was applied here equal to 0. And for this condition, one more condition is summation m equal to 0 was used for getting P1 and P2. Now we have, since we have P1, P2, what is the value of delta 1 and delta 2? So GPa to Newton per mm square will be this 202 GPa gigapascals is nothing but 202 into 10 raised to 3 MPa, or this is also nothing but Newton per mm square. MPa and Newton per mm square both are having the same values. Okay, 1 MPa is equal to 1 Newton per mm square. That is for that stress. I just converted this gigapascal to megapascal into 10 raised to 3. 202 into 10 raised to 3 megapascal. That itself is Newton per mm square. So 65. These are the modulus of elasticity for steel, and for aluminum it will be 65 into 10 raised to 3 Newton per mm square. Okay, so you can substitute these values for obtaining delta 1 and delta 2.
Delta 1 is 1.23 millimeter.
Okay, delta 1 1.23 millimeter.
Delta 2 is 0.396.
0.396. Okay, 0.396 delta 2 and delta 1 1.23 mm. Okay, so these are the values what you are getting. Others, if you have any other values, you can please tell, or if you have any difficulty in this. Okay, delta 1 and delta 2 are obtained now. What we actually require is what is the inclination of the bar. Okay, so what you have, this delta 1 minus delta 2. Okay, so that bar will get rotated. So what you have is delta 1 minus delta 2 divided by 0.5 or 500 mm. Okay, so it is in terms of mm. So this is the, so that is the inclination in terms of radians, this inclination. So delta 1 and delta 2. So this extension is more. So this is the inclination what you are getting here. That is what we have found here in terms of radians. Is that fine? Any difficulty in that part? Okay. Now let us take up this one more example on that composite section. I hope everybody is getting the answer for that previous problem. If not, you can unmute and ask what is the difficulty you are facing. Okay, in this case, what you have in this problem is, so a steel rod of 3 centimeter diameter is enclosed centrally in a hollow copper tube of external diameter 5 centimeter and an internal diameter 4 centimeter. The composite bar is subjected to an axial pull of 45 kilonewtons. If length of each bar is 15 centimeter, determine stress in rod and tube and load carried by each of the bars. Okay, so in this, what you have is, you are given with a steel rod, a solid steel rod, okay, whose diameter is 3 centimeter, and this is inserted inside a hollow copper tube. Okay, this is a hollow copper tube. So this solid bar is inserted inside this. Okay, so and this hollow copper tube, it is of uh, internal diameter 4 centimeter and external diameter 5 centimeter. Okay, so this is what you are having over there. It is something like this. Okay, so this inner this one, what you have see here, this is our solid bar. Okay, this one, and externally you have a hollow copper tube. Okay, is that clear? So these two bars, okay, or these two sections, they form this composite section over here. And what they have done is, they have applied a force of 45 kilonewton to this. You need to determine what is the stress in each of these bars, okay, in the steel bar, central steel bar, and outer copper tube. What is the stress in these two members, and also what is the load carried by these two members. If we find the stress, then finding the load carried by each member is not difficult for us. Okay, so first, what about the areas? Please check what area I have calculated. Will you get the same or any differences there in that? Okay, so these are the areas what we have. For this steel rod, it is a solid bar, okay, like this. So the diameter is 3 centimeter or 30 mm. So it will be pi by 4 into 30 square. That comes out to be 706.86 mm square. This is the area of what? This is the area of this steel bar, okay, AS. And same for copper, it is how much? This is area of steel, okay. And for copper, what we have is, this is the area of the copper tube. So it is a hollow circular tube. So what is the area? Pi by 4 into outer diameter square minus inner diameter square. So this is giving us what is the area of this copper bar. Okay, so let us say this is ACU, area of the copper bar. Now, what should be the stresses in the two bars? Okay, if you call them as sigma S and sigma C, okay, or even sigma CU, okay. So these are the stresses what we need to find. And if I go for finding the strain, what is the strain in steel bar and in copper tube? Okay, I can use this sigma S upon ES. Okay, so strain in steel bar will be stress in steel bar divided by its modulus of elasticity, sigma S by ES. Similarly, strain in copper bar or copper tube will be stress in copper tube divided by its modulus of elasticity. Okay, so this is the relation, Hooke's law again, what we have applied here. Stress by strain, okay, that will be nothing but modulus of elasticity E for any material. Within the elastic limit, this relation holds good. Okay, so this has been used for expressing the strain in both the bars. Okay, so what is the relation between strains here? Since both bars have been connected rigidly, okay, at their two ends, so what you should arrive is sigma S, strain in steel bar should be equal to strain in copper bar. Okay, or these strains, what you can obtain is, or say deformation, not actually the strain, the deformation. So what I can say is deformation in the steel rod and deformation in the copper tube, they are same, they are connected parallelly, so they should remain same. Okay, so what should be the deformation? If I go for finding that deformation, I can express this deformation in terms of this strain into original length. Okay, so this strain or deformation in the two tubes, if I equate them together, epsilon S is equal to epsilon Cu. Okay, or this can also be expressed as a sigma S upon Es is equal to sigma Cu by ECU. Okay, because these are the strains what we have obtained using Hooke's law, or what it tells you is what is sigma S in terms of sigma Cu, stress in copper bar in terms of stress in steel bar. The relation you will be able to obtain this. Okay, on substituting for this ES and ECU, Young's modulus of elasticity for steel and modulus of elasticity for copper. Okay, these are the values what are given to us. The modulus of elasticity here, ES is 2.1 into 10 raised to 5, ECU is 1.1 into 10 raised to 5. Modulus of elasticity are there, and also we have expressed what is the strain in both the bar in terms of stresses. Okay, when I equate these two strains, ES is equal to ECU. Okay, so I'll be able to put it as sigma S upon ES is equal to sigma CU by ECU, or sigma S will be ES upon ECU into sigma CU. Stress in steel bar will be equal to this modulus of elasticity of steel divided by modulus of elasticity of copper into stress in copper bar. Okay, this ratio normally we call it as modular ratio, ratio of modulus of elasticity of the two material. Okay, since these two are given to us, they have been substituted here in this expression, and we are able to get the expression for or relation between sigma S and sigma Cu. Okay, now what about the total force? The total force what is applied is 45 kilonewton, and that is shared by both the members, the copper tube and the steel bar. So whatever is the force in copper tube plus the force in steel bar, that should come out equal to 45 kilonewtons, or this 45 into 10 raised to 3 should be equal to sigma S into AS plus sigma Cu into ACU. Okay, so force you will be able to get it by multiplying stress with the area, whatever the area of the member is there. So in this sigma S into AS is the force in steel bar, sigma Cu into ACU is the force in copper bar. Okay, so stress multiplied by area, that is what is here for getting the forces in the two bars. So area we have calculated them, okay, previously. So on substituting the value of area and also using this relation between sigma s and sigma cu, what you get is these are the stresses what you have in steel bar and in copper bar. And how much should be the load? Yes, please check this stresses values and also tell me what is the value of load, force in steel tube and force in copper tube.
Sir.
Yes.
Yes, sir. Correct.
Okay. Can you give me what will be the value for forces PS and PCU? These are the stresses. What should be the value of this force in steel bar and force in copper bar? Anybody with the values of this forces? Anybody has got these forces?
Sir, force in copper is 1350.102 into stress of copper.
1350.10 into that you tell me how much it should be, how much you are getting that. Okay, so this is what the forces you find sigma s into s. Just multiply these stresses into the respective areas, so you should be able to get the values of forces in those bars. Okay, these are the forces in steel and copper bar. Okay, so I'll give these problems to you later so that you can practice on them. These are some practice problems from our from the previous question first based on composite sections. Okay, composite sections we have come across two different cases there, bars in parallel and bars connected in series. Accordingly, you need to apply the conditions. Okay, if they are in parallel, the deformation or strains in the two bars will be same. When they are in series, the force transmitted through each of the bar will remain same. So that is how we dealt with them. Okay. So one more next part is temperature stresses. Okay. So when there is a rise in temperature, any material either it will so normally when the rise in temperature it will expand, and with reducing temperature it will contract. So there will be changes in its length, volume. Okay. So that will also result in deformations in the material. Okay. So due to that deformation, or when these deformations are not free to occur, we encounter the stresses, and we call them as temperature stresses or thermal stresses. Okay. So this is the part wherein we'll be dealing with these temperature stresses. Okay. So so this is one bar which you have of length L, and we have one more property what we need to consider here is coefficient of linear expansion alpha. This alpha will give us what is the elongation of this bar with the increase in temperature, or contraction of the bar with reduction in temperature. With change in temperature, the length of bar will vary. If temperature increases, the length of bar will increase or it will undergo extension. With if temperature falls, the length of the bar will reduce or it will get contracted here. Okay. So under this case, when it is free to expand or contract,
Sir, you're muted.
okay, let us finish it. Tomorrow's class will take up that temperature stresses. You just try these three problems. Okay. So you can put your USN for the attendance in the chat box, only the USN, and then exit from here. We'll continue with that thermal stresses or temperature stresses tomorrow. If you have put your USN, I'll end this meeting. See that all of you have put your USN. 14 are remaining. If not, they'll be considered absent. Put your USN and exit.